All right, everybody, let's go ahead and get started. Just a reminder where we're at. We got a short week this week, obviously. No class on Wednesday. Have a great holiday, everybody. I'm sure you're all probably looking forward to that as much as I am. You do have an assignment out, so assignment 5 is still out. You have until December 6th to get that submitted. So I really hope that you've started on it. I know it's a busy time of year. I know that you've got other projects for other classes that you are also concerned about, and I understand all of this. I do think that this project is worthy of at least a little bit of attention before you go home for break. So if you have the time available, please make sure to take advantage of that. I'm still having my office hours tomorrow. In fact, I've got quite a bit of free time tomorrow. So if you want to come and have a chat with me about the homework assignment or anything else related to the class or even stuff not related to the class, I will be around tomorrow. I will be available to you in whatever capacity you need. So all I ask is that if you're planning to come outside of office hours, just shoot me an email or something so that I know you're coming and I can make sure to be there. But you know, if you wanted to get a good chunk of work done on the homework tomorrow, I am around, so I can help you out with any stuff that you've got related to that. Otherwise, we're getting close to the end here. When you get back from break, we got 2 more classes. We'll do 1 more class with new material, and then we'll do an exam review session on the last day of class, and then that's it. That's all you got besides the finishing up the homework assignment and submitting and taking the final exam. So that's what we'll be focused on after break. Does anybody have any questions for me right now about the current homework assignment or upcoming due dates and stuff like that? Yeah, what's up? You can use late days on homework 5 if you want to. It does not matter to me. Yes, go ahead and use your late days on 5. Yeah.
For 2 layers, what are some cases?
So there's only a certain number of there's a very limited number of them. We could actually enumerate all of them right now if we wanted to. So let's go ahead and clear this up. This board has been stuff all semester. That's great. I'll just use this one then. Where's the eraser? So it's important to understand that the spec is saying that you can have up to 2 layers of embedded stuff, right? So we start with a document, because everything starts with a document, right? So I can have up to 2 layers of stuff embedded within this document. And the only things that I can use to embed stuff are lists and documents. So I could have a list of documents. That's so 1 layer, 2 layers, right? 1, 2, 1 for the list, 1 for the documents. I could have a document that contains additional documents. Again, 1 layer, 2 layers, right? Or I could have a document that contains a list. 1 layer, 2 layer. The last possible combination, and I was just talking to somebody about this before class. I'm not entirely certain if this exists or not, would be a list of lists. I actually don't see any reason why that wouldn't work, but I don't know what the Mongo spec says. That would be something worth double checking. I certainly haven't seen a lot of lists with Mongo. Again, though, I don't really see any reason why it wouldn't be one. I do think that these other 3 things are probably much more common. I would agree with that. So that's what I mean by 2 layers. These are the only 4 possible combinations that you could expect to go 2 layers deep. Make sense? Any other questions about the homework assignment or anything else while we're on the topic before we hop into today's stuff? Alrighty, well, let's go ahead and begin. So today we're kind of wrapping up loose ends. We're at the point of the semester where we're just kind of wrapping up loose ends a little bit. We have spent the last few weeks talking about NoSQL, which has been very interesting because it takes a lot of the stuff that we've been talking about with our relational databases and kind of throws it out the window and takes a different approach, a different perspective. We're actually going to go back to the world of relational databases today. and talk about a different way of setting up relational databases that can be used as, you can think of as maybe an alternative to some NoSQL databases, although this is a very old concept that we're going to be talking about. It's not a new idea at all. It's been around for decades, still very much alive, still very much in use. In fact, has been picking up a lot of traction in recent years because the amount of data that is being collected and the amount of data that is being stored has just grown absolutely immense over the last few years. So this concept of data warehousing, still very popular, still very commonly used, but it is built on the world of relational databases. So put that NoSQL stuff to the side for a moment. Remember all of the things about relational databases that we talked about, tables with rows and columns that have one-to-many relationships, primary, foreign keys. That's the world that we're in today. So let's talk about this. A data warehouse is a structure, a way of storing data that has certain properties associated with it. And the point of a data warehouse is to, I'm going to actually start at the bottom of this one. We want it to assist in decision making. Or another way of thinking about it is that data warehouses are used a lot more for analytical types of things. So if I wanted to perform data analysis, data science types of activities, which of course are very big, popular fields in computer science these days, we're much more likely to see a data warehouse kind of structure than the other kinds of relational database structures that we've been talking about in this class. I'll explain what the differences between those are in just a moment. And so there are some properties that we want our data analysis, our data warehouse to have. It's going to be geared around a particular subject. So what is the actual topic that we're studying, that we're analyzing, as opposed to a process, right? As opposed to an operation that is being performed. We say that it's integrated, and this is actually a huge piece of data warehouse. Data warehouse wants to be a central repository for all of your information on a particular topic. So if I'm studying information about, let's say I'm a bank, right? And I'm studying information about accounts that I have at the bank. You can imagine that I probably got information about those accounts in many different spots. Each branch might have its own pool of accounts that it's responsible for, right? But in order for me to perform analysis effectively, what do I have to do? I have to collect all that information that exists in those satellite branches and pool it together in one single location. That location is a data warehouse. And so what are the issues involved with collecting all that information and integrating it together? That's something that a data warehouse needs to address. Time variant, meaning that time is almost always going to be of interest to us. When you think about analysis questions, a lot of times we're interested in how does this change over time? What can the last 10 years tell me about what the next 10 years are going to look like, right? So we're almost always interested in time. And then finally, we expect it to be very stable. The true purest form of a data warehouse says once that information gets put in there, it never changes, ever, right? In practice, that's a bit strict. In practice, we do have need to change pieces of information, sometimes either due to mistakes or other changes that might come along. But if we are going to change the data, we're going to do it in a very controlled way, And so these are all properties that we expect our data warehouse to have. These are all properties that suit us well for the types of tasks that we intend to accommodate with this data warehouse. So if we think about the pieces that a data warehouse contains and start thinking about this from a big picture level, we start with our operational systems. So operational systems being the day-to-day stuff. What's running our day-to-day stuff? There might be databases included in that, right? Maybe I have a user database that lets people log into my website. That's all operational stuff, the stuff that just makes it so our apps work. It's not related to analysis, it's just the functional stuff that makes our apps work. I want to get the data out of that and put it into my data warehouse. So what's the flow? What's the flow of data from my operational systems? It may not be a database. It might be the spreadsheet that your boss has kept on his computer for the last 30 years, checking all the random stuff, that happens in your department, right? We like to think that stuff like that doesn't exist, but come on, it does. It exists. I want to get a copy of that. I want to integrate that. I want to have all that data available to me in my data warehouse so I can analyze it, perform data analysis techniques. So we're going to go through a process. We're going to stage our data and run it through a process called extract, transform, and load, or ETL. You might have heard of this process. It is a very, very important part of setting up a data warehouse. Some metrics, like Ralph Kimball, who is sort of one of the godfathers of data warehousing, likes to say that extract, transform, load is probably 75% of the work of getting a data warehouse up and running properly. Absolutely a huge amount of effort. Why? Because we're taking data from many different sources and we're reconciling it with each other. I might have two different databases that have copies of data that don't agree with each other. We don't want that to happen, right? But in the real world, stuff like that happens all the time. So what do I do? Which copy do I keep? Can I merge these copies? Right? What do I do with that? We also have to deal with the fact that I've got data coming from many different sources. So I have databases, I've got files, I've got those old systems that have been sitting in the closet that nobody knows how they work anymore, but they still work, so we still use them, right? How do I get the data off of that and put it in this data warehouse, get it all in the same place? So we really have to take this data, integrate it all together, and clean it up. Make it so that it's ready to be used. Get rid of all of the imperfections. It takes a lot of work. There are some people whose job is to do that. That is their job, right? Such an important process. And once we're satisfied with that data, we can go ahead and load it into the data mart, which is really just a subsection of the data warehouse. So these are often going to be broken down by departments, where I don't necessarily mean departments like a computer science department or a sales department, but I mean departments in terms of the type of information that they contain, which actually could be sales, right, or computer science, but doesn't have to be tied necessarily to a physical department that exists in the real world. But this is the clean data that we want to provide access to our data scientists, to our people performing the data analysis. And it's going to contain a whole bunch of raw data as well as a bunch of aggregates. And this is what we're going to be spending a lot of time on today, talking about how this data is modeled. Gone are the ER diagrams that we talked about earlier in the semester. Data warehousing does not rely on those. Instead, relies on a technique called dimensional modeling. We're going to spend a lot of time chatting about why ER diagrams are not sufficient and why dimensional modeling can help us bridge that gap. And then finally, we might have some other applications sitting on top of the data warehouse to provide data mining or querying functionality for the people performing analysis. So if we wanted to envision this in picture form, right? Here's all of our operational systems over here. This is where the red box here in the middle is where the ETL happens. They should have made this box like way bigger because it's such an important process. Once everything has been transformed, it gets loaded into the data warehouse itself, which is integrated, actually siloed into various different departments called data marts, and then applications are built on top of those data marts. You might be looking at this and saying, well, this right-hand side over here with the data marts and applications looks very similar to the left-hand side with applications and databases. And you're right, it does. It looks very similar. The biggest difference that this diagram does not do the best job of capturing is a couple of things. One, over here, we're reading data in. I'm pulling data in from an application, storing it in my database. Whereas here, these applications are extracting data out of the database for analysis purposes. So the direction's a little bit different, but also the structure. You see that these function-oriented systems are labeled with an acronym, OLTP. And over here, the data marts and the data warehouse are labeled with an acronym, OLAP. And so what those acronyms, we'll talk about what those stand for in just a little bit, but what those are really telling us are that the models are different. The way that this data is modeled is very significantly different from the way that this data is modeled. So let's chat about that. Online transaction processing is what we've been talking about for 2/3 of the semester. When we go through ER diagrams, when we look at those examples, that's online transaction processing. We want to run lots of queries that are relatively small and quick. We want to run queries that are geared towards functionality that I wish to perform. Users logging in, users logging out, users making posts, right? Those are all geared towards use cases. Those are all geared towards stories. How do I implement the functionality for this story? I'm not necessarily interested in historical data all that much. Maybe a little bit, but I'm not going to go back. Like, when's the last time you looked at your Facebook profile from 10 years ago? I did it a couple weeks ago, and I really regret it. It was terrible. It was a much different person. Don't judge me on that guy. Right? It just doesn't happen very often. We're interested in the immediate past, for the most part. So much so that if Twitter shows me a tweet from last week, I'm like, what the hell? Like, come on, like, it's old news. And then this is maybe the biggest point. This data in these online transactional databases are usually geared towards very frequent updates. Oh, I'm making a post, that's an update, right? I'm inserting a new record into a table or multiple tables. Oh, I clicked like on that, well, there's another record that's getting entered into a table, right? Oh, I made a friend today, all right, let's update the records to indicate that, we are now connected. I am now following you, or whatever the case may be. We are updating this information very, very, very frequently. Anytime I interact with the website, basically, I'm making a record. I'm updating a record. I'm keeping track of stuff that is happening. Whereas the type of database that we're talking about today, a data warehouse, is geared towards an analytical approach. So the number of queries that I run against that are going to be fewer, but they're going to be huge. I want to extract a large amount of data. For analysis purposes, the more data I have, right, the better, stronger conclusions I'll be able to draw. So I'm probably going to be pulling lots of data, lots and lots of information. I'm not going to be updating that data. In an ideal world, I would never update it. In the real world, I am going to update it, but only periodically. And most of the time, those updates are going to be inserting more information, not changing the existing data, but just adding more information. Here's this month's sales data. Let's add that back in so that we can use that for analysis, right? I'm going to use lots and lots of historical data. We're going to go as far back in time as we possibly can. And then, here we say this data is subject-oriented. It's not geared towards a particular process. I don't want to know how to log somebody in or make a post. I want to see how the number of posts users make changes over time, right? The questions that I'm asking, hoping to get answers for, are geared towards a particular topic, particular subject, not for the purposes of enacting a process. That's not to say that this is better or worse than transactional processing. They just both have different situations that they're trying to address. And so, here's some example queries that you might run against a database. These are very business-oriented. They don't have to be business-oriented, but, things to pay attention to. Product that has been the most profitable in the past 10 years. So we're going way far back in time. And we're asking about products specifically. We're not asking, how do I sell these products? What's an effective way of shipping these products? We're actually asking about the products themselves. Which week of the year do we have the most sales? If I only have 1 year's worth of data, I can get an answer to this question, but it's going to be a pretty weak answer, right? I want to have lots and lots of historical data. Are the sales of this product increasing over time? So we're really looking at big picture, analytical types of questions. All right. I've already touched upon these a little bit, but just to more formalize the issue of data integration. Actually, the one at the top of the list is maybe the most complicated one to deal with. Redundancy of data is a perennial problem. How do you even know when the data is redundant? How do I know that this record in this table is referring to the same thing as this record in this table? How do I figure that out? You might be asking yourself, well, just look at the primary keys, or, and in some cases that might be right. But you have to remember that while I truly, truly hope and wish for all databases to be designed very well and be very consistent, the reality is that that's just not going to happen. There will be mistakes made. There will be databases that were created 30 years ago that we have just kept using even though they're totally busted, right? And I still need to have a meaningful way of getting data out of that. So yes, there might be easy ways to solve this problem, but in reality, it's a lot more complex than that. So this is a huge part of data integration, just trying to figure out what redundant data exists. Trying to combine data from different sources. So if I have existing databases, those are pretty easy. Documents can be kind of easy, but the trick there is that not all documents have the same format. So, Excel files all follow the same format, but if I'm looking at just some random text dump, what's the format of that? I don't know. And then, of course, legacy, old stuff has its own tricks to deal with. We're looking at data that's designed with operational systems in mind. For example, I'm interested in tracking data based on how my users use the system, not necessarily for analysis purposes. The data that I want to connect to perform the analysis might be different than the data that I want to collect just for day-to-day use. Quality and then volatility. How often is this data actually changing over time? All things that can cause problems with the ETL process. And so to expand on this a little bit more, ETL actually usually looks like a data flow. I have a data flow that starts with a source and ends with the destination. My destination is almost always going to be a data warehouse. The source could be any number of things. And then in between the source and the destination, I'll have a series of transformations. I'll have a transformation to check for duplicates. I'll have a transformation to check for missing or poorly formatted data, right? I'll have a transformation to change the format of the incoming data to match the format that I expect the destination to have, right? So it becomes sort of a chain of transformations that get applied. Cool. All right. This is the big topic for the day. Multidimensional modeling. So some of this is a little bit of review. Relational databases that we are used to talking about, right? The databases that work with ER diagrams often use normalized data. We talked about the three normal forms, right? What those forms are, how we normalize the data, and the reason why we normalize data is actually this was an exam question, I believe, to some extent. It eliminates redundancies, gets rid of duplicates. That's the big thing. And the reason why getting rid of duplicates is so important is that it makes insertions fast, right? If I have the same piece of data in two different places, that means I have to insert that same piece of data more than once. And I have to update that same piece of data more than once to maintain consistency. So by eliminating redundancies through normalization, we have really optimized the database for fast insertions, fast updates. At the expense of what? What is the price that we pay for normalization? What do we have to give up in exchange for this fast insertion and updates, eliminated data redundancy? What's the cost? Yeah.
One cost is slower read times via more joins.
So By eliminating redundancies, I have to create more tables. More tables means more joins. More joins means that my reads are going to be slower. That's exactly right. Normalization increases the efficiency of inserts and updates at the cost of decreased efficiency for reading data. And if you think about it, right, in a lot of ways, that's okay with us. Again, the reads that we're performing are already going to be pretty small. I know I keep leaning on this example, but if I'm logging into a website, I'm literally looking for one row in the users table that matches the person being logged in, right? It's not a huge chunk of data that I'm pulling back. It's a very small chunk of data. So the fact that it takes a little bit longer, it's like, yeah, okay. All right. We're willing to make that sacrifice. We're talking about data warehouses now, though. Why is that no longer an acceptable sacrifice to make? The amount of data that I'm reading is now huge. It's gigantic. In order to perform effective analysis, I need lots of data. Lots and lots and lots of data. So this trade-off that we've made is now hurting us. It's not helping us anymore. It's hurting us. The good news is that there's a simple solution, a simple idea to get us around this fact. So here we are, just kind of contrasting the way that ER diagrams see the world versus the way that multidimensional model sees the world. One table per entity. We talked about this when we made ER diagrams right on the board. We talked about this. We're optimizing for updates, whereas this multidimensional model is going to have not an entity, but it's going to have one fact table per process. So we haven't talked about fact tables yet, but that's how we're referring to our model now. We are really trying to we're not interested in data redundancy anymore. In fact, we're going to say, you know what, maybe a little data redundancy isn't so bad after all. That's our new outlook on life with the data warehouse. We're just going to tolerate a little bit. This data shows up in multiple spots. Okay, all right, I'm okay with that. Because we want to maximize understandability. And I would argue that this does that if I denormalize my data, if I have duplicate information in many spots. Think about what that entails. I now have a row where instead of having to follow a bunch of foreign keys to figure out what this row is talking about, it's all just right there. Right? The foreign keys are gone. I'm not normalizing as much anymore. I don't worry about foreign keys. It's all just going to be right there in the row. So we're really optimizing for data retrieval. We're optimizing for reads. If I have duplicate copies of data, I no longer have to follow foreign keys to find the information that I want. It's just right there. Right? If I have 100 copies of the same piece of information, it's going to be much quicker and easier for me to find one and give it to you. That's the theory. That's the idea. So it's a really different view of the world that de-emphasizes normalization. I'm no longer interested in strict third normal form types of normalization on my database. And so the design changes too. Now instead of entities and relationships, we're talking about fact tables, facts and fact tables. We'll talk about each of these in detail coming up. We also have dimensions, dimension tables. Facts contain things called measures. We'll talk about what those are in a little bit. And dimensions contain hierarchies. We'll see some examples. And the designs that we're making now are not ER diagrams. They're not normalized or normal form types of models. We're trying to design a star schema or a snowflake schema. So let's talk about each of these pieces and the purpose that they represent in our model, and then we'll take a look at the model as a whole, put all the pieces together. The purpose of a fact table is to record the actual quantifiable information that exists. So this is the raw data. This is the numeric data, right? So what process, what subject do we want to study? In this case, we're doing the classic example of sales, And so the stuff that we are studying, the stuff that we are recording is how much stuff did we sell and what was the amount in dollars that we sold, right? Notice those are both numeric. Those are both quantitative, right? I can actually definitively measure those things. In fact, we call these measures. The fact table contains measures, where a measure is some quantifiable piece of data. So every row in our fact table then represents one of these things happening. In this case, we're talking about sales. So every row in my fact table represents a sale that has taken place. How much things did I sell? How much was that worth? I should be able to record that data about every single sale that I place. Yeah. So I already introduced the concept of measures and the fact that they are numerical. A lot of times they're also additive, meaning they can be aggregated together, which will become important a little bit later. So if I wanted to know the total sales for a given month, right, I could simply just add up all of the dollar sales amount for sales that took place in that month, and that would give me an accurate reflection, right? Fact tables are said to contain true data, and we actually say that they're quite sparse. We've seen that word before. Where do we see that word come up before? Sparse. What were we talking about? Remember? Yeah. With the index. Yeah, what did it mean in the context of an index? That's good. Yeah. So does my index, my actual index structure, have an entry for every entry in the base table that we started with? This is a similar idea. When I say that it's sparse, I know we haven't talked about dimensions yet, but what I really mean is that not every date may show up here, right? Not every product may show up here. Or perhaps a more realistic example is not every combination of date and product might show up here, right? I don't expect to have an entry for every single date and product in store necessarily. That's what I mean by sparse in this particular context. Maybe we'll double back after we talk about dimensions a little bit. That might make a little bit more sense. But you can see that the things that I was just talking about, date, product, and store, they're labeled as foreign keys. So primary key, foreign key relationships haven't gone away all entirely. We still have some, right? We're still doing some joins. I never made any promises about eliminating them entirely. But these are now pointing to our dimensions, which we're going to talk about in just a moment. And so facts come in different flavors, 3 different flavors primarily. I'm only going to focus on the top one, the transactional fact, which is probably the simplest and easiest to understand, and also probably the most common. Anytime an event occurs, I enter a row in my fact table. So anytime I make a sale, there's a row in the fact table to represent that sale. It's a transaction. I gave you something, you gave me something back. I gave you a product, you gave me money in this case, right? It doesn't have to be that way. The other types of facts to watch out for are snapshots. So snapshots, the classic example of a snapshot is used for inventory. If I want to know like the inventory of a warehouse or the inventory of a store, I can record how much of everything I have at the end of a day, at the end of a week, or whatever. So I'd have one row in there for the inventory of my products at the end of every week or the end of every month. And if I wanted to see how much stuff I had, at a given time period, it's just as simple as locating that row. So it's a snapshot of the current situation. And then an accumulating snapshot is a very specialized kind of niche version that is good for examining things going through a pipeline. So I can track how fast a shipment is moving from the warehouse to the shipping center to actual transportation on a truck, right, to local delivery. I can accumulate those dates over time and see how fast things are moving. But the most common one that you're going to see, and the one we're going to spend our time talking about, is the transactional fact. Any questions so far? Sorry if I'm going too fast. I've had like 3 cups of coffee today. My bad. Let me drink some more. Any questions? All right. One last thing about fact tables before we get to dimensions is this idea of granularity. In fact, I would argue this is maybe one of the most important things to consider when talking about designing or using a data warehouse. We're really asking the question. Granularity is asking the question, what does a single fact mean? Or what does a single row in the fact table represent? And it's related to the primary key. It's related to the primary key. Well, wait a second. What is the primary key? There's nothing marked here as the primary, there's nothing marked as the primary key, right? I see foreign keys. I don't see a primary key. Hold on to that question. I don't want you to answer it right now. I want you to think about it for a few minutes while we keep talking. I'll ask you again in a few minutes if you have an idea as to what that primary key should be. Back on the topic of granularity, we really got 2 choices. I can have a very small amount of granularity, meaning that the data that I'm recording is a very small chunk, represents a very small chunk of data, or I can have very large granularity. Large granularity would be recording things on the sale level, right? Like if I go to Schnucks and I buy a bunch of groceries, a large grain way of looking at that would just be looking at the total at the bottom of the receipt. How much did I make on that particular purchase? A small grain way of looking at that transaction would be to record every single thing that I bought, right? Which is also on that receipt. In this sense, I would actually argue that one of these is better than the other. Do you think it's better to record things on a detail level or at a more large scale level? Which way are we going to prefer in most instances? Remember what our goal is with the data warehouse? Our goal is to provide analysis. That is our goal, right? I want to ask analytical types of questions and use data to help me answer those questions. Yeah?
It seems like we prefer small grain. We'll use a lot of data and probably a lot of pre-processing power, but it'll allow us to ask any sort of analytical questions we want.
Yeah, so small grain data is definitely the right answer here. And to consider why, think about, too, whether these operations are reversible or not. If I have small grain data and I want to get the large grain data out of it, I can do that, right? I just have to group it all together and add it up. Does it take work? Yeah, it takes a little bit of work. It takes a little bit of effort, but it's doable. If I tell you that I went to Schnucks and I sold $50, or I spent $50, and you want to try and figure out what I bought, that's an impossible question, right? I mean, knowing me, you could probably guess that I bought a bunch of goldfish crackers and ice cream because we go through those things like water in my house. But, there's nothing, just, based on the total sale, there's not enough information to answer that question. So almost always better to capture things in a small grain. What's the downside of this small granularity? There's always a cost, right? There's always a price. What's the price that I'm paying here? Storage, yeah, it's definitely a big, and performance too, you said, and I agree with that as well, because having to perform those aggregations takes some time. Storing one row of data to represent the entire sale is a lot less space than storing one row for every single thing that I bought. There's a lot more space involved. But if you haven't already kind of gotten the picture from data warehousing, at this point we're not concerned about space. There's been another thing involved that is hopefully giving you that clue, right? The denormalization, the tolerance of redundancy is also going to use a lot more space, right? So if data warehouses cared about space, they have a funny way of showing it, because they're right now are just letting the inefficiencies with space pile up. And again, we do that because we're trying to optimize the read performance. All right, let's talk about dimensions. So the facts tables are remember, the quantifiable stuff, the stuff that I can actually examine and record, and measure in a quantifiable way. The dimension tables provide the context. They literally the who, what, when, where, how, and why. So where did this sale take place? When did this sale take place, right? Who was the person that you interacted with to make this sale? All of these kinds of things. What was being sold? What was the product that was being sold? So everything that I expect to see in a dimension table is going to be contextual in nature. So if you think of measures as being quantitative, right? Things that I can definitively measure, dimension tables are the opposite of that. They're not going to be quantitative. They're going to be contextual in nature. They're going to be discrete values. There could be numbers here, right? So if I look at weight is very clearly a number, and you might be saying, well, hey, that's something we can quantitatively measure, correct? Shouldn't that be in the fact table? And in some cases, the answer to that might be yes, that actually should be in the fact table. But if we're thinking about things in terms of sales, does the weight matter towards sales? Usually not really. It matters towards things like shipping, right? And so if that's what I'm analyzing, then maybe this is going to be a measurement in that particular data warehouse. But this can be something in something that's used to describe context as well. These tables are going to be very, very, very large. Meaning, and when I say large, I mean the number of columns that they have is going to be absolutely immense. Just so many different columns. Basically, if you can think of a different way to describe, here we're talking about products, right? If you can think of a different way to describe a product, I'm going to make a column for that and include it. I want to think about this in every single possible way that I can. Why? Again, remember our goal. I want to perform analysis. What kind of analysis do I want to perform? Well, I need to be prepared for just about anything, right? I need to be prepared for just about any kind of analysis that somebody might come up with. I don't want to artificially limit the kinds of analysis that I can perform. So I'm going to include as much information as possible here so that I can pick and choose what kinds of variables I want to analyze, right? And produce different types of analysis based on different situations. Okay. So yeah, dimension tables are used to create groups. They're used to provide constraints on things. I'm only interested in products that, are made by this manufacturer. That's a constraint, right? They're used to provide labels. If I construct these dimension tables appropriately, I can use the data in this table as the labels on my analysis output, as the axes on my graphs, as the descriptions on the labels on my graph, or whatever the case may be. So it's very important to have very descriptive dimension tables that provide as much information as possible. Now let's take a step back. I asked you a question a few minutes ago. I asked you to think about it. Here we actually see my dimension table has a primary key. It's called a product key. Product key. So that's labeled as a dimension, or as a primary key here. And if I go back to the fact table, you can see that product key, right? There's the foreign key side of it. So there is a one-to-many relationship between my fact table and my product table, just like there's a one-to-many relationship between the date and the store tables as well, right? What is the primary key of this table, though? It has one. Definitely has one. It's not labeled, though. It's a special kind of primary key. I know we've talked about it before. Yeah.
I think it's a compound primary key, but I'm just trying to figure out what field it's based on.
Yeah, composite primary key. Yeah, that's right. That's right. Composite primary key. That's exactly right. What fields would it be based off of? So that's a good question. I think there's a natural, I mean, if you just look at this right now, you can kind of see a grouping of columns, the foreign keys. And I think in some senses, this actually looks a little bit like tables that we've seen before with the ER diagrams. What table does this remind you of? With the multiple foreign keys involved, composite primary key. What table does that remind you of that we talked about way back when we were doing ER diagrams? What kind of relationships are we expressing in this multidimensional model? Looks and feels a lot like, not a Zelda table, but, oh yeah, linking table. The hero's name is Link, not Zelda. All right, so the foreign keys are kind of a clue, right? The foreign keys are kind of a clue to that nature. Is this a linking table? No, it's a fact table. I don't want to make that equivalency, right? That's not the point I'm trying to make here, but it does share some commonalities. The composite key, the primary key, is the combination of the foreign keys. If you think about it, it kind of makes sense, right? What's the relationship between date and product? Well, I'm going to have many products sold on many dates, right? I'm going to have many dates where I'm selling many products. So you could argue that there's kind of a many-to-many relationship across there. But more importantly, I wouldn't use that terminology with a multidimensional model, that many-to-many terminology. I would actually use granularity. This is the important terminology. I know I'm bouncing around a little bit, but this is such an important concept that I wanted to come back to it. Now that we understand what dimension tables are, now that we understand what the primary key is, how would I express granularity for a fact table? I would express it as the foreign keys that it contains. I would express it as the dimensions that are connected to it. Or in other words, the granularity of this table, this fact table, I would express as the quantity and sales amount for a given date of a given product at a given store, right? The granularity is a function of the dimensions that are contained in my data warehouse. Does that make sense to everybody? So then how do I change the granularity? If I wanted to make this even smaller grain, what could I do? There's actually something I could do. If I wanted to look at this at a lower level, how would I change the granularity of this table? Or I can make it larger too. If I want to make the granularity of this table larger, what would I do? Any ideas? So larger grain means fewer rows that contain, bigger picture data, right? And smaller grain means more rows that contain more detailed information. Right? What if I'm interested in sales over, not just on a given day, but like, do I sell better in the morning or the afternoon or the evening or at night? Is that an example of smaller granularity or larger granularity than what we see here? Smaller, right? In fact, which dimension am I talking about when I describe that? The date, right? I'm no longer recording things on a day-by-day level. I'm recording them on a time-of-day level, right? By the hour. I mean, honestly, if you wanted to go down to the second or whatever, you could. That would maybe be a little overkill, but so I can change the granularity by changing how I describe these dimensions. Looking at these dimensions on a lower level, or if I wanted to do larger granularity, I could change date to be month, right? Or if I wanted to talk about granularity on the store level, larger granularity could be, instead of a single store, I could look at a single city or a single region, right? Or on a smaller level, I could look at it not as a single store, but maybe a department within the store. Right? So I can change the granularity of a fact table by changing the dimensions that I'm talking about. The two are very intricately related to each other. excuse me. In fact, the description that I was just giving to you is an example of a hierarchy. A hierarchy. So we talked about dates, right? Dates have, of course, the date itself, which is part of a week, which is part of a month, which is part of a quarter, which is part of a year, part of a decade, part of a century, epoch, whatever, right? As far as you want to go. That's a hierarchy. That's a hierarchy. Or another classic hierarchy that we expect to see. This one's based on location. So we are currently in a city, St. Louis, which is in a state, which is in a country, which is on the planet Earth and the solar system and the Milky Way galaxy, right? However far we want to take it. There's hierarchies there, and these hierarchies are important for us to pay attention to and be aware of. So let's talk about that in a couple of ways. Where are these hierarchies going to show up? What I just described to you, right? The date hierarchy and the location hierarchy. Where in my model, which tables do I expect those to appear in? There's only two choices: fact or dimension. Where are these hierarchies going to show up? Is this an example of contextual data that tells me who, what, when, where, and why, or is this an example of quantitative data that I'm measuring definitively? It's a dimension. This is dimensional data. This is context. Location, that's where, right? That's context. My dimensions are going to contain hierarchies. They're going to contain hierarchies. The other thing is to ask, well, why? Why do we care about these hierarchies? Why is this important to us? Anybody have any ideas as to why it's important to keep track of these hierarchies? Think about in terms of the bigger picture here. What is this data warehouse for again? What are we trying to do? Trying to answer analytical questions. So how does this hierarchy help us answer analytical questions? These are natural levels, right, at which to perform analysis. And the levels affect each other. If I want to know the sales that occurred in the state of New York, I have to take the sales that occurred in all of the cities in New York and combine it together and aggregate it, right? So these hierarchies have a nice natural relationship. These hierarchies are going to be natural places for us to perform analysis. And there's another important role for hierarchies that is going to come into play in just a little bit. All of this gets us to the idea of performing the actual analysis using a concept called data cubes. So using this term dimensions is meant actually quite literally. We are going to construct cubes where the axes of my cube, so a cube implies 3 dimensions, right? So the axes of my cubes are going to be dimensions from my data warehouse. So we had 3 dimensions before. We had date, product, and store, correct? So one axis would be the dates, one axis would be the products, and the third axis would be the store. Now, in practice, while humans work very well with 3 dimensions, computers are not bound by our 3-dimensional limitations, right? Computers can handle however many dimensions we can throw at it. So in practice, our data warehouses are going to have a lot more than 3 dimensions. Common figure for dimensions is going to be anywhere from a dozen to a few dozen. I haven't really seen any that have more than 50 dimensions. Would be like on the high end, the very high end of the number of dimensions I would expect. I would say most probably fall in the 10 to 20 range of dimensions. And for a computer, that's not a problem. But then, of course, if we want to view it, we're limited to 2 to 3 dimensions. But let's talk about what we can actually do with these cubes and how we can use them to perform analysis. These are the units of data that we're going to be performing operations on in order to answer the questions that we care about. So let's take a look at a picture. This almost matches the example that we saw on the previous ones, but here's a cube. On this axis, I've got the product or the item type. On this axis, I've got time, right, or date. Actually, it's listed as quarters, but potato, potato. And then on the third and final axis, I've got locations. And you can see at the intersection of those, I have numbers. These are cells in my cube, where the way to interpret that is this 31 is the number of phones that were sold in Q2 in Vancouver, right? Just the intersection of the dimensions tells me how many how many things were sold. So the measures go in the cells, the measurements go in the cells, the dimension is on the axes. Everybody with me so far? Because there's more that we can do with these cubes. They're actually fairly flexible. Here's an example of if you wanted to try and approximate a 4-dimensional cube, right? So it's just a series of 3-dimensional cubes where each cube has a 4th dimension. So here, supplier is the 4th dimension, I guess, or manufacturer, whatever the case may be. So I just replicate the cube for each value on the 4th dimension. And actually, using this mechanism, you could abstract this out. 5 dimensions would be a two-dimensional grid of 3-dimensional cubes, right? 6 dimensions would be a cube of cubes. It gets all very meta very quickly. In practice, though, we don't do this. We let the computer handle that. In practice, what we care about are the operations that I can perform on these cubes. What I can do with them. What can I do with these cubes? How can these cubes help me reach my goal of data analysis? So there's a few operations that are commonly performed on these cubes. The first one that I see here in the upper right is called a slice and dice, which are 2 different operations that are very similar. A slice is, I start with a 3-dimensional cube and I literally just take a slice out of it, right? I look at one of my dimensions, I hold all the other dimensions constant, and I just take the slice out. So a slice is really reducing the number of dimensions that I am currently looking at by holding the other ones constant. So for example, if I look at this cube that I started with, I could look at the New York slice, right? By just taking this slice of the cube out. I'm holding this dimension constant. I'm just saying, forget about the other ones. I'm just interested in New York. Give me this slice. And then look at the sales of New York over quarter by item type. A dice is a similar operation, but instead of taking a slice out of the cube, I just take a subcube out. Right? So it could be, tell me all of the sales for New York and Toronto over Q2 and Q3. That's going to be a smaller cube, right? A subcube. I always think about cooking. That's where the terms come from, right? Slice versus a dice, making smaller cubes or making slices. It's the same concept. It's the same idea. Rolling up and drilling down are kind of complementary opposites of each other's. So if I roll something up, I'm taking a dimension and I'm moving up the hierarchy. So here we have years on the time dimension down here at the bottom, and I have decided to move up the hierarchy to all time, right? Show me the sales across everything from the beginning of time to now. That's moving up the hierarchy. That's a roll-up operation. How do we do that? I take all the values that are in the cells and I just add them together. I aggregate. I aggregate things. If you want to do it by location, right? Let's do it by country instead of by city. Take all the cities that are in the same country, add up their values, aggregate them together. That's a roll-up operation. Drill down is the opposite. All right, here I am at years. What if I really wanted to know by quarters instead? That's going to take these numbers and then split them up into smaller chunks. So you can see that I actually have more cells on the result. So roll up and drill down are based on the hierarchies, and that's another reason why hierarchies are important to be aware of. Here's just textual information about slice dice. Drilling down, rolling up. Actually, this slide's a little bit confusing. I should have changed this. Drilling down, or actually I should just take, drilling down and rolling up are just opposites of each other. This slide does not do a good job of explaining that. I will modify this a little bit and repost it because it's gonna bother me if I don't do it. Sorry about that. So how do we use these operations? We can think of all of our cubes as being at a starting point, where the starting point is the fact table, right? The base granularity of my facts table. That's our starting position. So then I have to figure out, all right, what operations am I performing on this cube to answer the question that I care about? I want to know the sales of all products. I'm sorry. I want to know the sales of all products in Chicago. Right? What operations do I have to perform on a cube? Well, I have to roll up on time to get to all time sales, and I have to slice out all of the cities that aren't Chicago. That's how we would describe that operation, right? These are the true building blocks of dimensional modeling. This is the whole point. Cubes are the goal. Dimensional modeling is the tool that we use to achieve that goal. And a lot of database systems now are actually including the dimensional modeling syntax. So I can actually say, slice this cube, roll up this cube, right? I can do all of that stuff. But the fact of the matter is that really most of our databases are built around relational databases. And those databases were built for online transactional processing using ER diagrams. And so what's more common is to see our dimensional models converted into a relational style. So I'm going to use the existing relational setup of tables and relationships to define my dimensional model. And so that leads us to the concept of a star schema. We're making a physical implementation of our multidimensional model using relational database concepts. So the fact table is going to be, I'll actually show you a picture that'll make it easier to visualize what this actually looks like. But the model itself is pretty simple. There aren't very many tables. It's very easy to add stuff to the tables. Here's what it looks like. The fact table is in the middle. The fact table has foreign keys pointing. Now this has date key labeled as primary key. I don't think that's right. I think that should be a foreign key. I think they got these swapped on this image. I'm sorry about that. I think those got swapped. But anyway, the fact table is in the middle, and then the dimension tables are all linked to the fact table via primary key, foreign key relationship. So the idea is it looks like a star, right? One thing in the middle and a bunch of spokes coming out of it. Notice that if any joins take place at all, the fact table is involved. Fact table is at the center of the universe, and the dimensions are orbiting it, right? So this is a relational way of expressing our multidimensional model. And then, applying this is as simple as determining the SQL query or cube operations that you want to perform and abstracting the information out, where these are going to become the actual data that I see on an analytical report, for example. We're almost at the end. All right. One final thing to talk about, and then we've got some review questions to wrap up the day. There's an alternative to a star schema that kind of revisits the basic premise that we mentioned at the beginning of class today, which is that we're not going to normalize stuff anymore, right? That was kind of the premise that this all began with. Was we're not going to normalize stuff anymore. We're going to embrace the redundancy. In some cases, space is a concern. So it would be nice then to, apply maybe a little bit of normalization. Just take a smidge of normalization to get rid of some of that data redundancy. We're making a little trade-off here, right? I've got a lot of data. I'm willing to use a lot of space, but maybe I can eliminate some of the redundancies and still have a pretty efficient database. So Snowflake schema says, all right, we're going to start with the star schema, and then we're going to normalize. We're going to normalize some of these tables. Specifically, we're going to normalize the dimension tables a little bit. What do we have in the dimension tables that could be normalized? What's a natural target for us to normalize in our dimension tables? It's something we've already talked about today, quite a bit, in fact. Where is a source of redundant data within our dimensional tables? What do dimension tables contain that's a source of redundant data? Starts with an H, ends with an hierarchies. The hierarchies, if I'm tracking location, which I think we actually have here, right? Street, city, country. So for every row, I'm recording the country. Every single row, which means for everything that happens in the United States, I have United States, United States, United States, United States, many, many, many times. That's redundancy, right? That's an example of redundancy that normalization would typically get rid of. And so what a Snowflake schema says is, all right, I acknowledge that redundancy is there. Let's try to get rid of it a little bit, at least, and still maintain the general dimensional structure. So it says we're just going to normalize our hierarchies in our dimension tables. And so instead of having, one table for a dimension, I might have multiple tables for a dimension where the second, or it could even be third or fourth, or if I have multiple hierarchies, this might actually have multiple branches, right, for the different hierarchies involved. That's where it gets the snowflake-like appearance. I can normalize those a little bit to help with the data storage costs. Again, at the cost of performance, because now I'm introducing more joins into the mix as well. So it's a balance. You have to make that trade-off accordingly. For a long time, there were two schools of thought here. One school of thought really emphasized star schemas. That was propagated by Mr. Ralph Kimball. The other school of thought really emphasized snowflake schema, saying no, a little bit of normalization is okay. And I don't even remember the guy who was arguing for this, which tells you which one won that battle. Some people still use these. They still exist. You'll see them out there in the wild. I don't want to dismiss snowflake schemas outright, but the star schema has really caught hold as the dominant standard for dimensional modeling, especially as the cost to store stuff has just really decreased. Space is cheap. Hard drives are cheap. Space is cheap. So that redundancy really, really does not matter as much as it used to. So you can kind of see the trade-offs, the pros and cons between the two approaches, star schemas and snowflake schemas. The biggest thing that star schemas have going for them is it's relatively simple. Small number of tables makes it very easy to analyze the structure at a glance. Yeah. All right. I have some review questions that we're going to spend the rest of the time. How much time we got left? We got 10 minutes. Perfect. I'm going to spend the last 10 minutes going through some review questions. But before we do that, does anybody have any questions for me about anything that we've talked about today so far? Let's do some check your understanding questions. In fact, we have enough time. I'm going to give you guys a few minutes. There's 2 slides, 6 questions. If you've been paying attention, these questions shouldn't be too crazy. I'm going to give you a few minutes. I'm going to do like 2 or 3 laps, give you a few minutes to talk to your partners about these, and then we will do these today. I will ask you these before we wrap things up today. All right?
So we have this idea of measuring the universal concept, but we also have stuff to yes. Would it be fair to say, because I'm just trying to think.
Well, measure is a fact. When you say measures and facts, I feel like that's the same thing.
Is what I'm saying. Yeah. So, like measure versus dimensions, there can be
There can be, yes.
Would it be fair to say that measure values are unique and or maybe as where I don't think dimensions are shared between humans and are not
They're definitely dependent on the dimensions are definitely shared between rows and factors. I'm not sure if that's exactly what you're trying to say, but I think an even better test would be: do I plan to aggregate this value? Do I ever plan to sum it up or average it or perform some kind of analysis on this number? The answer is yes. That is a measure. Versus the answer is no, and that is okay. Very good. Cool. Thank you.
So very small. It says, well, yeah, but then I mean, that's one. But
all right. None of these questions should take more than a minute or two to chat about. So let's see how many we can get through in the few minutes that remain. First question on the list. What will typically be larger, a dimension table or a fact table? Actually kind of started you out with a little bit of a tricky one. Anybody want to give me an answer? Dimension table or fact? How many of you think a dimension table is going to be larger than a fact table? And how many of you think a fact table is going to be larger than a dimension table? The rest of you don't care? Which, you know, fair enough. Fair enough. It's almost Thanksgiving. I get it. I agree with all of you, even the ones who don't care. I actually do care. The question, as it's written, I think could be satisfactorily answered either way. It depends on your definition of bigger, which I know sounds like a very political way of answering the question, but it's true. I think a dimension table could be argued as bigger. Why? What's large about a dimension table? Has a lot more. We can take a look at an example, right? Back here. Dimension table has a lot of columns, massive number of columns. So if you wanted to say a dimension table is larger in that sense, I would absolutely agree with you, compared to a fact table, which has relatively small number of columns in comparison, right? However, a fact table I would expect to be larger because lots more rows. In fact, it's continuously growing, whereas a dimension table might grow a little bit, but I certainly wouldn't expect it to grow as fast as a fact table would. The true answer, though, of like which one is larger in terms of like bytes stored, I'm not sure you could tell one way or the other, right? It would be hard for me to say one way or the other, and could actually change over time. So if I ask you a question like this on an exam, which I won't, but if I did, your answer to me could be, you know, dimension table is larger because of this, or fact table is larger because of this, which is fine. Or you could even say, compared to what? I don't know, like
insufficient information. All right. Let's see. How much time? I don't want to keep you guys later than our scheduled time. We got a few minutes left. Let's see. We don't have enough time to do all this. Let's do this one. What's the relationship between dimensions and facts? 1-to-1, 1-to-many, or many-to-many? Dimensions and facts. What's the relationship? It's 1-to-many. Which side's the one and which side is the many? Fact can have, so a fact can have many dimensions, but that's not quite the same thing. Your statement is correct, but does not quite answer the question of which side's the one and which side's the many. I mean, we can look at this. The fact that this is labeled as a foreign key tells us that the fact table is which side? One or many? Many. The fact table is the many side. So one product can appear in the fact table many times, right? Or I can sell one product many times, right? I can have a sale occur at the same store many times, right? Many times. One store is involved in many sales. Another way of thinking about the problem. So there is a one-to-many relationship there. The one is the dimension, the many is the fact table. We'll end on this one because I've only got like 2 minutes left. Why is it necessary for measures to be numerical? Or actually another question, which I think is even more interesting, is can you think of an example of a measure that is not numerical? I don't know if any of you got this far or thought about this question. Does anybody want to throw out an example of something they think should go in a fact table that's not numerical? Example of a measure that's text-based or not quantitative? So, no takers? That's actually okay with me because I can't think of any either. I cannot think of any either. I was actually talking to somebody about this during my labs, right? To really answer this question, consider what measures are used for. Consider how they fit in the realm of cubes, especially when I consider performing operations on a cube. What happens to those measures when I perform operations on the cube? They get added. They get, split up into pieces. I'm performing mathematical operations on them. That is a necessity. That is a necessity for me to do. So if I'm performing aggregates on something, it's got to be numerical. It's got to be additive. Those are the kinds of things that we're looking for our measurements. Those are the kinds of things that I want to see in my fact table. If I have things that are not additive, that I don't plan to aggregate, those belong in the dimension table. Those are contextual information. We didn't get to all of these, but maybe we'll do a little review after break. That's all for today. Have a great holiday, everybody. If you are going to miss me over the week, come say hi to me tomorrow. We can say goodbye during office hours and chat about the homework. You're not going to miss me, though, and that's fine. Have a good break. What's up?